Hello, everyone. Welcome back to this online class. My name is Francis Okech, and my YouTube channel is Professor Francis Okech. Today, we are going to look at Calculus 2, and our main topic is on integration by parts. We need to know what is integration by parts, and we look at some examples involving integration by parts. So first of all, I want us to recall the product rule. Take note about the product rule of differentiation. In the product rule, you said that when you want to differentiate with respect to x, that is a product of u and v, then the result was that you keep u constant, then differentiate v with respect to x, plus now keep v constant, differentiate u with respect to x. So if I multiply by dx, we are going to get the uv is equals to u dv plus v du. I have multiplied both sides by dx, so the dx will cancel so that I get what I've written in red. Or I can rearrange it so that I have this. I can make u dv the subject, or u dv is the same as derivative of u times v minus v du. And then integrate both sides. So you can just say, therefore, the integral of u dv is equals to the integral of derivative of u times v minus the integral of v du. You know, where integration and differentiation are inverses of each other. They are inverse processes. So that the integral and derivative, those ones are inverses of each other, so they'll cancel. So we can just see that, therefore, this is now written as uv minus the integral of v du. So you can just write hence the integral of u dv is the same as uv minus the integral of v du. Look at what we have found. This is what you are calling the parts formula, the formula that you use in integration by parts. This is called the parts formula. Parts formula. Now, when do we use integration by parts? You realize that we're integrating a product. There is one of the functions is u, another function is dv. So this parts formula is usually used when we are integrating a product of two functions. So I can comment here that the formula is used when integrating a product of two functions. Product of two functions, and either function is not, and either function is not the derivative of the other function. So when you have such kind of integrand, then you think of integration by parts, where the integrand is a product of two functions and none of them is the derivative of the other. The only way to do that is via integration by parts. So we have to decide which function to take as u and which other function to link to dv. So there's always a rule that we use to decide on which one is u and which one is supposed to be dv. So we can write here that we must decide, we have to decide which function to choose as u or to take as the function u, and which one to link to dv, and which one to link to dv. That is the task in the integration by parts. Once you know u and you know dv, then to proceed is very easy. Now, how do we choose u? That is the question. There's always the order that we are always using to decide on which function is u and which function is dv. So we are always using, right? Use the what we are calling LIATEC. Use the LIATEC rule to decide or simply to choose the function u. What is the meaning of LIATEC? Let me explain it here so that you can be able to understand it better. Let me take this up. So LIATEC means this. L there stands for logarithmic function. I denotes inverse function. I can give you an example, e.g. This you could talk of ln x. Here you could talk of sine inverse of x. The other one is A. What does it mean? It is algebraic function. An example is x squared. That is an algebraic function, or simply a polynomial. Algebraic is also a polynomial. Then we have t. What does it mean? T there means trigonometric function. An example, you could talk of cosine of 2x, trigonometric. Then we have e. The e there denotes exponential function. E.g., can talk of exponential 3x. And lastly, we have the c, which means the constant, e.g., 2. So this is the order that we'll follow to decide on which function is supposed to be u. So you go from, if it is LIATEC, you go in this manner. Whichever you encounter first, that will be u. If it is like this one, it will now be in this manner. You start from L going towards C, L towards C, and you decide which one do you encounter first. That is what you are going to link to U. So once we know what LaTeX means, then this is what you're going to follow, that the function U must be a function that we encounter first according to that rule. As I have explained, that is either from L going towards C. Then the remaining functions together with the dx will form dv. I'm going to give you an example. An example to use that rule. For example, we may have this integral. In part A, I want just to see which one is going to be u and which one is going to be dv. Let's say we have the integral of x cubed times ln x dx. Now, you need to classify these functions. X cubed is algebraic. It's a polynomial. Ln x is logarithmic. So look at our rule, LaTeX. Between L and A, which one do you encounter first? When you move from L towards C, you encounter L first, then A follows. So here, you're going to say let our U be the L. That L is ln x. Now, what you realize that now we remain with x cubed and dx. Those ones will form dv. So our dv in this case will be equal to x cubed dx. You see the way I've linked them? You start by choosing u. Once you have decided on which function is u, automatically the remaining functions will form dv. Another one, let me give another one to show how we can choose u and dv. So let's say you're integrating exponential x. This is multiplying cosine of x dx. Let's classify these functions. This one is exponential, and this one is trigonometric. So again, look at our LaTeX rule. Between E and T, which one do you encounter first? I can see T appears before E. So we are going to say now let U to be that trigonometric function because it's the one that we encounter first. So you say let U to be equal to cosine of x. Now what do we remain with? Exponential x dx. That will form dv. So in this case, dv will be equal to exponential x dx. I'm just showing you how to choose u and v. Then in the examples, I'll tell you how to apply the formula now. Let me give you another one. Part C, let's say you want to integrate ln x dx. Remember, this can be written as the integral of 1 times ln x, because I simply need a product of two functions. One is a constant, ln x is logarithmic. So when you look at LaTeX, you encounter L before C. So you say let U be equal to ln x. And now we remain with 1 times dx, that will form dv. So dv is equals to 1 times dx. Very important. Let me give you another one where we have the inverse function. We can talk of the integral of sine inverse of x. So the last one, but D, let's say you want to integrate sine inverse of x dx. So to be able to work out that, this is what you are going to do. You rewrite this as the integral of 1 times sine inverse of x dx. So let's classify these functions. Again, 1 is a constant. And here we have the inverse. Between I and C, you encounter I first. So you're going to say let U be equal to sine inverse of x. Now we remain with 1 times dx. That will form dv. So dv is equals to 1 times dx. So having explained how to choose your function u and dv, what next? That is the question that everyone is now asking. That now we know u and we know dv. What are we supposed to do next? So the next thing is you differentiate u with respect to x and make du the subject. You know how to differentiate? Yes. Once you have done that, you need to integrate dv with respect to x to get v. So like here, the next thing you're going to do here is now differentiate u. You will top of du dx is equals to, here it is 1 over x. So you make du the subject, so du is equals to 1 over x dx. And this other one you integrate dv. Also you integrate x cubed dx. So when you integrate dv, you get v is equals to, when you integrate x cubed, remember power rule, that will give us x raised to 4 divided by 4. Don't write the constant of integration. So take note. You differentiate u and make du the subject, integrate dv to get v. That's the next step. Then another thing that you need to do, but again, you need to take note that when you're integrating dv, don't write the constant of integration. I hope that point is taken. Don't write the constant of integration. Why are we not writing the constant of integration? That's a question that somebody might ask. The reason is that a single constant will be added to the last step, the final answer. Remember, at this point, we don't know the answer. We will only add the constant when we now know the answer. So there's no need of having so many constants. That's very important. Now, once you've done that, you are now going to substitute u, du, v, and dv into the parts formula. Substitute those results that you have found into the parts formula. And then simplify to get your answer. So, when do we terminate the process? Because you see, in the parts formula, let me take you back to the parts formula. In the parts formula, you realize that, of course, we are going to substitute. We now know u and v, but still on the right-hand side, we have the integral of v du. So you still need to integrate it. You will find that at some point, you will need to apply another integration by parts to work out the integral of v du. So when should you terminate your integration by parts process? So to terminate the process, terminate it only if the last integrand can be integrated, or repeat the process if the last integrand still contains product of functions, or collect like term if the last integrand is the same as the starting integrand. I'm going to explain using an example so that you can be able to understand that concept better. And a point you need to take note of, in some integrals, these LaTeX rules might fail. So I want us to take note of that. I can write a note that if the LaTeX rule fails, that if you cannot use it, if it fails, then what are you supposed to do? Then you write, then you must be a group of functions. You must be a group of functions that can be differentiated easily. That can be differentiated easily, and dv must be a group, and dv must be a group of functions that can be integrated easily. So I want to explain that using another integral here to just to show you that in this integral we cannot use the LaTeX rule. So let me give you an example to illustrate this note here that we have made. So you can talk of e.g., let's say you want to integrate x times exponential x over 1 plus x, and this is supposed to be squared, integrate with respect to x. You see here, you don't know, we have how many functions? There are 3. So here you cannot use LaTeX rule because here we have 3 functions. One of them is algebraic, that is x. Another one is exponential. And what about 1 over 1 plus x squared? Where do we classify that? That is the question. So LaTeX rule cannot work in this integral. So what you do, check the function that you can easily differentiate and check the function that you can easily integrate. Of course, you start by checking which one can you easily integrate. That is what you link to dv. So in this case, this thing can be written as, let me write, it is the integral of x times exponential x times 1 over 1 plus x squared dx. So what I will do here, I can easily integrate this 1 over 1 plus x squared. So that will be our dv, and then this one will be u. So we are going to say let u be equal to x times exponential x. And automatically our dv will be the other function. So you can say dv will be equal to 1 over 1 plus x, and this is squared dx. That point is very important. You see, you can still use integration by parts even if you don't use the LaTeX rule. So that is very important. Now, I want us to look at some examples here on how to apply integration by parts. Maybe 3 examples should be enough. The first one is you want to integrate x cubed times ln x. So examples. I want us to evaluate the following integrals. Evaluate the following. Evaluate the following integrals. The first one is, let us call it A. The integral of x cubed times ln x dx. As usual, let, of course, L here is logarithmic, x cubed is algebraic, a polynomial. So our u will be ln x. That is the one we encounter first. L before A. So let u be equal to ln x, and our dv will be the remaining, that is x cubed times dx. So that is x cubed dx. And so we now differentiate u. So du dx. When you differentiate ln x, you get 1 over x. Or make du the subject, du will be equal to 1 over x dx. Here you integrate dv, both sides, integrate x cubed dx. You see, this is integral, this is derivative, so they are inverses of each other, so that we remain with v is equals to x raised to 4 over 4. Don't write the constant of integration. So now the parts formula, therefore, the integral of x cubed ln x dx is now the same as uv minus the integral of v du. uv, that's the parts formula. Let us substitute our u and our v. So this is equals to u times v. Remember, look at our u is this, our v is this one, multiply the two. That will be, our u is ln x, our v is x raised to 4 over 4, minus the integral of v, that is x raised to 4 over 4, times du, which is 1 over x dx. And how else can you write this? This is the same as 1 over 4 x raised to 4 ln x minus 1 over 4, as a constant, the integral of x cubed dx. And now you can integrate that using power rule, so that our final answer is now equal to 1 over 4 x raised to 4 ln x minus 1 over 4 x raised to 4 divided by 4 plus a constant c. And so this can be written as 1 over 4 x raised to 4 ln x minus 1 over 16 x raised to 4 plus a constant c of integration. You see how it is very simple? As long as you know u and you also know dv, then your work becomes very easy. I want to give you another one. Talk of part B. In part B, we're integrating x squared sine 2x. Let me talk of sine 3x dx. So what do we do here? As usual, we need to classify these two functions. X squared is algebraic. Sine 3x is trigonometric. Look at the LaTeX. Which one do you encounter first? We encounter A before T. So you write let U be equal to x squared, so that our dv will now be equal to sine 3x dx. Differentiate u, so this will imply that derivative of u with respect to x, that is equals to 2x, or make du the subject, or du is equals to 2x dx. Let's integrate dv. Both sides integrate sine 3x dx, so that you know the integral and derivative are inverses, and so we'll remain with v is equals to what did we differentiate to get sine? It was negative cosine, so negative cosine of 3x divided by 3. Don't write the constant of integration. So go back to our integral. So you can now say that therefore the integral of x squared sine 3x dx is the same as uv minus the integral of v du. So when I multiply, our u is this, our v is this one. Let's multiply. That will give us negative x squared times cosine of 3x over 3. That's uv minus the integral of v du. Our v is negative cosine 3x over 3, and our du is 2x dx. This we can simplify. So let me take this up. When we simplify, we are going to get negative 1 over 3 x squared cosine of 3x plus 2 over 3, because that's a constant, the integral of x times cosine of 3x dx. That's what we have. Again, you realize that for us to integrate the integral on the right-hand side, I can still see there's a product of two functions of x. Here, x is algebraic, and cosine of 3x is trigonometric. So again, you make another substitution. So you let another u be equal to, in fact, I can write it this side. Let me wrap that. So we wrap this one. Again, we are going to say let u be equal to x and dv be equal to cosine of 3x dx. So that when you differentiate u, this means that we differentiate u with respect to x, so du dx, that will give us 1. Or you make du the subject, du is equals to 1 dx, 1 times dx. And then integrate this other one, dv will be equal to the integral of cosine 3x dx. Ask yourself, what did you, of course here we'll have v, so you need to ask yourself, what did you differentiate to get cosine 3x? That is sine 3x over 3. So again, we work out this integral. We now work out this integral separately, and then we'll substitute our answer once we have the value here. So I can call the whole of this equation, call it equation star, or we'll come back later. So we can now say that therefore the integral of x times cosine 3x dx is equals to, again it is uv minus the integral of v du. When we substitute, what do we get? uv, our u is x, our v is this one, so it is x times sine 3x over 3, then minus the integral of sine 3x over 3 dx, which you can write as 1 over 3 x times sine 3x minus 1 over 3 the integral of sine 3x dx. And now you see you can easily integrate sine 3x. So our final answer here is 1 over 3x sine 3x minus 1 over 3. When you integrate sine 3x, you get what? What did you differentiate to get sine? You differentiated negative cosine. So this will be negative cosine of 3x over 3. And now remember, here now you can write the constant c. Or you see, before we write c, we are still going to substitute back there. We'll write c at the end of it, at the end of everything, once you have the final solution. So this you could write as 1 over 3 x sine 3x plus 1 over 9 cosine of 3x. So this answer, we now substitute it into the original integral. See the answer we have found here. This one, we take it back here to get the final answer in the original integral. So I'll rewrite the original integral. So it means the answer we have found, we multiply by 2 over 3 to get our final answer. So we can just say here that they have, let's use another color. Therefore, the integral of x squared sine 3x dx is the same as negative 1 over 3 times x squared cosine of 3x plus 2 over 3 times the answer we found, that was 1 over 3 x sine 3x plus 1 over 9 cos 3x. And now you now write the constant c of integration, because this is the final answer. We can also simplify this. Let's see, when you simplify, what do you get? This will give us negative 1 over 3 x squared cosine of 3x, then plus 2 over 9 x sine 3x plus 2 over 27. And that is supposed to be cos 3x plus c. So that's what we have as our final answer. You see here we have used integration by parts twice. So that's very important. I told you at times you may be using it twice or even 3 times, etc. Let me give you another one that as another concept to illustrate. Let's call it part C. Another problem is part C. You want to integrate exponential 2x times cosine of x dx. Exponential 2x times cosine of x dx. So again, using the parts formula, let's classify these functions. This one is trigonometric, and no. That is exponential, not trigonometric, exponential. And this one here is trigonometric. LIATEC rule, we encounter t before e. So automatically our u will be cos x. So let u be equal to cosine of x. That is our u. So automatically the remaining will form dv. So our dv is exponential 2x dx. That's what we have. Now differentiate u and integrate dv. So we are going to differentiate, you write du dx. When you differentiate cosine, you get negative sine x, or make du the subject, so du will be equal to negative sine x dx. Integrate dv on both sides, so integral of exponential 2x dx. This will give us v is equals to exponential 2x, and this is over 2. Excuse me. So now we now go back to the parts formula, substitute uv, du, and dv. So you can now say that therefore, the integral of exponential 2x times cosine of x with respect to x can now be written as uv minus the integral of v du, which when we substitute, u is this one, our v is this, so let's multiply. That will give us 1 over 2 exponential 2x cosine of x minus the integral of v, which is exponential 2x over 2, and our du is negative sine x dx. I am going to simplify that to get this. When you simplify, you get 1 over 2 exponential 2x cos x plus another 1 over 2 the integral of exponential 2x sine x dx. Still, we need to use the parts formula. So again, decide on which function is supposed to be u and which one is supposed to be dv. So again, here we have exponential Here it is trigonometric. So we again say let u. Our u will be equal to now the trigonometric part, that is sine x. Our dv will be the remaining, that is exponential 2x dx. So when you differentiate u, what do you get? You get du. Of course, you're going to get du dx is equals to derivative of sine x, that is cos x, and then you make du the subject, so that will give you cosine of x dx. Integrate dv to get v is equals to exponential 2x over 2. So again, we apply the parts formula to be able to work out this integral. Apply the parts formula here to work it out. So therefore, our answer will now be equal to 1 over 2 exponential 2x cos x plus 1 over 2. Then here now we'll write uv minus the integral of v du. Remember, there will be a constant c of integration later, but I don't need to write it here. We'll only write at the last step. So this is equals to, I can use another color, 1 over 2 exponential 2x cos x plus 1 over 2 uv. Our new u is this and our v is this, so let's multiply. That will give us 1 over 2 exponential 2x times sine x minus the integral of v du. So that will give us 1 over 2 integral of exponential 2x cos x dx. When you substitute, you get that. Let me open the bracket. This is equals to 1 over 2 exponential 2x cosine of x plus 1 over 4 exponential 2x sine x minus, this will now be 1 over 4 x, now the integral. So let me write integral minus 1 over 4 integral of exponential 2x cos x dx. Look at what we have here. That integral can never end. It will not end. You'll always get a product of exponential and trigonometric. You see, we have performed integration by parts twice, and still the integral cannot end. But there's something you need to take note of. Look at the integral that we started with, exponential 2x cos x dx, and still we have it here. Those are like terms. So collect like terms. So this one, you take it to the left-hand side. Remember, on the left-hand side, we have exponential, because it's this one. It is this that we are saying is equals to that. So it was the integral of exponential 2x cosine of x dx. It is that integral that is giving us what we have on the right-hand side. So this integral and this integral are like terms. I am going to take those integrals to the left-hand side and then simplify. Then we see what we are going to get. So let me take this to the left-hand side. What are we going to get? So you say, therefore, the integral of exponential 2x cos x dx When you take it to the left, it now becomes plus 1 over 4. 1 over 4 times the integral of exponential 2x cos x dx. Now, on the right-hand side, we now remain with these two, these ones. That's what we remain with. So it will be 1 over 2 exponential 2x cosine of x plus 1 over 4 exponential 2x sine of x. Excuse me. So, you see here we have 1. 1 plus 1 over 4. That is 5 over 4. So you can write here, or 5 over 4 times the integral of exponential 2x cosine of x dx. What will it be equal to? It's the same as what we have on the right hand side. Of course, I can factor out the exponential 2x. So this is 1 over 2 cos x plus 1 over 4 sine x. Exponential 2x is common, so I factor that out. That's what we have. So you now make this integral the subject. So divide by, or simply multiply by 4 over 5 on both sides. So you can say, hence, the integral of exponential 2x times cosine of x dx, we make it the subject. So we are multiplying by 4 over 5. So that will give us 4 over 5 times 1 over 2 cos x plus 1 over 4 sine x times exponential 2x. So this is the final answer, and so now you can write plus a constant c of integration. I said that constant, you introduce it at the final step where you know the final answer. So this thing can as well be written as, if I simplify, I want to factor out 1 over 4. When you factor out 1 over 4, we'll have 1 over 5 2 cos x plus sine x times exponential 2x plus a constant c. And so that is our answer for that particular integral. So I have explained how to apply the parts formula and the various methods or the various cases that you might encounter and how to go about those cases. You see the examples 1, 2, 3 that I have looked at, they are very special and they tend to give you some idea on how to deal with integration by parts. So try to look for more questions in this area and use parts formula to be able to evaluate them. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we will look at other techniques of integration. Bye-bye.